Continuing our previous discussion on the interference of light, in this session, let us go deeper into the topic. Here, there are two sources of light which are known as coherent sources, and these waves of light are emitting from these two sources. Hence, these waves are also known as coherent waves, and the waves are specified by the function this as y1, this as y2, and these two waves, while traveling in the space, they intersect at each other at this point. Intersecting each other at this point. This is a point of intersection. At this point, the interference takes place, which alters the amplitude of the wave. The amplitude of the resultant wave at this point is different, and the waves before and the waves after remain same in their fundamental properties. The interference takes place only at the point of intersection. It is the point of interference. And before going to the subject, let us understand once again the meaning of coherent sources in geometrical form. This geometry says wavelength, there is a one wave I represented. So that is two waves are there in the same. This is one wave and another wave. Both of them have same wavelength. But what difference you are finding among them? The amplitude difference. It has more amplitude, less amplitude. More amplitude, less amplitude, positive and negative. But wavelength remains same. And there is no phase difference between them. Here, having same wavelength, the two waves may have same amplitude or different amplitude like this. These two waves are called as coherent waves. That is one geometrical form. Another geometrical representation of coherent sources is this. Here again, two waves are there. There is one wave, another wave, and the wavelength remains same. The difference is one is lagging behind the other. The wavelength remains same, and they may have same amplitude or different amplitude. But the wavelength remains same. We see the difference. It is phase difference. That is called as phase difference between the two waves. And this phase difference phi, if it remains constant over a period of time while traveling along the x-axis, they are known as coherent sources. In these two sources, coherence, there is a phase difference which remains constant over a period of time. But these two coherent waves which have no phase difference is zero. That is the difference. With which we understood the real meaning of coherent sources of light. Now, this wave function, that is wave 1, wave 2, it is from the source S1, it is from the source S2. This wave function is given by this equation. It is known as sinusoidal wave. this wave function is given by this equation, the same sinusoidal wave, and assume that they have same amplitude. A amplitude remains same, and among them there is a phase difference which is a constant phase difference. Then they are coherent sources, which may be 0 or some value. They become coherent. And this is y1 wave function before intersection. Wave function after intersection remains same. And wave function here before intersection and after intersection remains same. At this point, the wave function is different. That wave is called as resultant wave. The resultant wave due to interference. Let us find out the equation for the resultant wave due to interference. There are two possibilities: waves of same amplitude or waves of different amplitudes. Here difference first one, waves of same amplitude, waves of different amplitudes. A1, A2. Equation remains same. And in the previous class, we have derived the equation for the resultant wave for the waves having same amplitude. Already we have derived the equation. The equation is this equation. Derivation follows y1 plus y2. Two vectors. You get a vector. Wave function is a vector. And we have done this already using that is the principle of superposition, of course, addition. The principle of superposition applies to all vector additions. The two vector addition. This is what we get from we call it from the previous class. This AR is resultant amplitude of the resultant wave YR at this point. And this is sine function remains same, difference pi by 2. This pi by 2 is now the phase difference between, it is the phase difference between y1 and yr. The phase difference between y1 and yr. Look at the difference. What is pi? The phase difference between y1 and y2. Pi by 2 is the phase difference between y1 and yr, where AR is the resultant amplitude. And this resultant amplitude is known from the previous class, 2a cos pi by 2. 2a cos pi by 2. It is resultant wave. And this is at this point phase difference between y1 and yr. This is what you have done in the previous session. In this session, let us find out or let us derive the equation for the resultant wave due to interference. And those two waves have different amplitudes, A1 and A2. These are the two equations. For the resultant wave, follow the same principle of superposition, that is yr equals y1 plus y2, and addition, vector addition, that is y1 plus y2 difference. We get this equation. Now we have two, this is a1 and a2, there is no common a. So we have to apply the trigonometric knowledge to solve this equation. It is little bit complex compared to the previous one. In this equation, look at this, concentrate on the second term, a2. So let us write this as sine of a plus b. We can apply this standard equation sine of a plus b for this sine function. You can assume this as A, this is B. We know sine of A plus B formula, standard form, sin A cos B plus cos A sin B. Apply this and see what we get. A2 is common and inside sine of this into cos of this. Sin A cos B, cos A sin B. A is kx minus omega t, B is, we applied this formula, we get this equation. And further simplification, remove this bracket, it will apply to this term as well as this term. Further simplification, in this equation, here we have one common factor, sine of kx minus omega t. Sine of kx minus omega t is common factor. We can take out this as common factor. Remaining among these two terms, a1 here for first term, second term a2 cos phi, a2 cos phi, common factor. And in this last term will remain same, a2 into this sine and cos like this. This is again the complex equation. It is become more complex. It requires some special trigonometric technique to solve this equation to arrive at AR. Here A1, A2 is there. How to arrive at AR, resultant of these two waves? We need a special trigonometric technique. You have to follow this procedure. Let us write this equation as 1 and let us consider this. Suppose to have like this. Now we can call this term as AR cos theta. A1 plus A2 cos phi equals AR cos theta. Let us call it as this. Then understand later why you do so. Here difference is here amplitudes of the individual waves, here amplitude of the resultant wave, and eta, that is eta is the, that is phase difference between y1 and y2, and AR, that is theta, is the phase difference between y1 and yr. y1 and yr. y1 and yr, phase difference theta. New symbol has come. This theta is different from pi. We are introducing theta. Similarly, we can write A2 sin phi equals AR sin theta. Again, the same thing. Sin theta is. Let us call this as like this. Equation 2 and equation 3. Put them into equation 1. Let us put this equation and solve afterwards. It becomes, when you put into the equation 1, this becomes AR cos theta. This becomes AR sin theta. Equation remains always. So this becomes AR cos theta. It becomes AR sin theta after substitution into this equation. And we get this equation. Look at this equation. AR is common. We can take out AR as a common factor. Remaining is, this is sin cos, that is sin cos like this. So this is similar to this equation. What is the expansion, or it is the reverse of this. Here this is of this form, sin A cos B plus cos A sin B. This equation, when here is common factor. We can write this as, in simplified form, sin of just A plus B. It is just reverse of this. This is A, this is B. So sin of A plus B. This entire thing is sin of. AR is there, common factor, you have taken out common factor AR, it becomes sine of kx minus omega t plus theta. Here theta is the b. Sine A plus b it becomes. We have arrived at the final equation. What is via resultant wave? The equation. So it represents the resultant wave at the point of intersection. Resultant wave, where AR is the resultant amplitude. And what is theta is here? Theta is the phase difference between y1 and yr. Difference theta. This is the equation. In this equation, we need to understand what is AR1 and what is theta. We go for solving them. Now to solve AR, solve for AR, resultant amplitude. Let us go back. Equation 2 and 3, using this. You have to square them. Squaring left hand side, right hand side. Squaring left hand side, right hand side. Square them and add them. Let us see what we get. Squaring and adding the equation 2 and 3 and see what we get. Squaring left hand side plus left hand side. Square and then add up. Squaring this. Squaring this. A square into sin square. Right hand side, squaring this. AR square cos square theta. AR square sin square theta. When you add them, sin square theta plus cos square theta becomes 1. It is common factor. So remaining is only AR square, right hand side. Now we come to this AR square. Let me interchange left hand side as this side, right hand side as this side. And expand this as well. So AR square, expanding this and see what we get. Apply A plus B whole square formula. A1 square plus A2 square cos square phi here plus 2 into A1 A2 cos phi. A plus B whole square formula plus A2 square sin square phi is there. Here we have cos square is there, sin square is there. A square is common. When you take out A square common factor here, cos square plus sin square becomes 1. Here it becomes 1. This into 1. So remaining is this. A square, AR square is this. What is AR? It is because square root of this. A1 square plus A2 square plus 2A1 A2 cos phi. What is phi? The phase difference between the wave 1 and wave 2. We have arrived at this AR. Resultant amplitude of the resultant wave is this is the expression. We have arrived. That is, this is how you have solved this. AR is this. Now you have to solve for theta. What is theta? Is this. To get it, you have to divide the same equation. Use the same equations. Divide the equation 3 by 2. Here 3 is this. This divide by 2. So when you divide this divide by this left hand side. What is that? A2 sin by A1. And right hand side, when you divide this, sin theta by cos theta is tan theta. The AR cancel right hand side. I have taken this is one side, interchange the sides. So this is becomes tan theta when you just divide them. One side, other side remains this divided by this. This is in the form of tan theta. What is theta? Theta equals tan inverse of the function like this. This is a function, tan inverse of this function. This is theta. What is AR? This is a resultant wave equation due to interference. That is, AR is a resultant amplitude. Theta is the phase difference between Y1 and YR. Y1 and YR, that is resultant wave, theta. And theta is given in form of, what is that? Eta. We need to know what is theta in the form of eta, pi, like this. So sin pi divided by sin cos. It is the difference between the phase difference between y1 and y2. So it is a form of eta, pi. Now the geometrical representation of this theta and eta, theta and pi. What is the geometrical representation? If this is a1 and a2, the function, first function and second function, the amplitudes are vectors. The addition of these two vectors follow this law of parallelogram. So this is the resultant amplitude, what we get. So this is the resultant amplitude, this is the A1 amplitude, this is the A2 amplitude. Magnitude of A1, magnitude of A2, this is the magnitude of AR. This pi is the angle between these two, and theta is the angle between AR and A1. Look at this. First wave and the resultant wave, theta. Here we understood what is the difference between theta and pi. Geometrical representation of the functions theta and pi. So this is all the equation. Equation is the resultant wave equation due to interference, the generalized form of equation, where maybe the amplitude may be same or different, generalized form. So this is a generalized equation of this resultant wave. With this equation, using this equation, now you can write the conditions for the constructive interference as well as destructive interference. So let us continue with the previous class, that is next class. Thank you.